Good day, stat students. So today we're going to talk about 6.2, and we're going to get into the probability distribution of a continuous random variable. So, what you have to do with regards to continuous random variables is that you got to associate probability of a continuous random variable with, believe it or not, an area under a curve. Area under a curve. So remember this problem? Excuse me, the heights of all U.S. males are, adult males are bell-shaped with a mean of 70 and a standard deviation of 4. And so we said mu is equal to 70, sigma is equal to 4, right? And then we put it on a graph. And notice here that I have 70 in the middle. And then since the standard deviation is 4, we have 70, 74, 78, 82. 66, 62, 58. And that first axis is in terms of x. And then I put the z-scores underneath it. And so that's telling us that 74 is what? 1 standard deviation from the mean. 78 is 2 standard deviations from the mean. And it's greater than the mean because it's positive. And then over here, 58 is 3 standard deviations from the mean, but its value is lower than the mean because its z-score is negative. So remember doing that? And then we shaded in the middle part, and we used the empirical rule. And we said about 68% of the data is located between, 66 and 74. And so, meaning a z-score from a -1 to a +1. So my question to you is that, let's change it around. Instead of saying what percentage of the data that's sitting there, okay, you can translate this into a probability. And so let me change the problem around. Let's say that we randomly pick a person out of here, and an adult U.S. male, and so we randomly pick a U.S. adult male out of this group. Okay, what's the probability that he is going to be between 66 and 74 inches tall? All right. Well, what's your intuition tell you? Since we have 68% of the data sitting between here and here, what's the probability of this happening? And hopefully you say, well, it's approximately 68%, and your intuition is correct. Okay, and so what you have to realize is this: is that this concept that we're talking about is exactly the same, believe it or not, as a pie chart. Okay, you're all used to looking at pie charts. Okay, this concept is no different. Okay, so for instance, let's say that, let's go back to our example here with male heights. Let's say that I wanted to know the probability a male is going to have a height between 77 and 78 inches. Okay, notice in our graph that's pretty small. Okay, and if we shaded this in, okay, notice, did we shade in just a little bit of the graph, or did I shade in a lot of the graph? Hopefully you say, well, I shaded in on just a little bit, right? Well, what would that be, as far as a pie chart went? What's the equivalent of that? Well, just shading in just a little bit of it, okay? Now, this one right here, you would say, okay, maybe I shaded in 1 or 2% of the entire graph at this point, as far as the pie chart went. Well, if I just shaded in just a little bit, okay, now it's a little bit harder because it's not a circle, it's an irregular shape here, okay, but it's the same concept. If I shaded in just a little bit, that would be 1 or 2% of the graph. Same holds true with the pie chart, right? Or let's say that I went ahead and wanted to shade in from 62 to 78. So not only would I have that middle shaded in, I would also have everything else in white that's in between there shaded in. So pretend I shaded in all of that, and I shaded in all of that, okay, along with stuff in the middle. And so imagine that we've shaded in everything from here to here, okay, and we should know that's about 95% of the data, right? Well, how would that look on a pie chart? Well, let's see, that's basically, I pretend that I just kind of carved out about 5% of it, and then the rest of this was shaded in. And you would look at the pie chart and you go, oh, okay, well, I've shaded in a whole bunch, right, in the pie chart. Okay, and you would say, okay, well, since I've shaded in a whole bunch, that means the probability should be pretty high. And that's all we're doing. It's just that it's a little harder to do with this because it's an irregular shape versus a pie chart. All right, but the concept is the same. It's just that instead of enclosing it in a circle, what are we doing? We're just enclosing it underneath a curve. That's it. That's the idea here. The second concept with regards to probability distributions of continuous random variables. Here's the second concept. So remember this one? Not remember this one, but I gotta remind you of something, that x is absolutely positively a continuous random variable. And you'll see why I'm saying that. Here's the second part to this. The probability that x is equal to any value, believe it or not, it's equal to 0. Okay? And the first time people hear this, generally speaking, they don't like it, but it's absolutely true. Probability that x, which is a continuous random variable, is equal to any specific value is nothing. So let me give you an example. Let's say that you weigh yourself, and the scale indicated 120 pounds. All right? My question to you is, do you really weigh exactly 120 pounds? Well, maybe you got a precise enough scale, and the scale actually said, instead of 120 pounds, it said 120.2. You go, okay, well, that's reasonable, right? But my question to you is, did you weigh exactly 120.2? Probably not. Let's say that your scale could take this out another decimal place. Probably it couldn't, but let's say it did. Did you weigh exactly 120.24? Probably not. So you take out another decimal place. Did you weigh exactly that? Probably not. Take out another decimal place. Did you weigh exactly that? Probably not. And you take it out 7 more decimal places. And did you weigh exactly that? Probably not. Why? Because you could always take it out another decimal place. Now, when you work with weight in pounds, in pounds or whatever, kilograms or whatever, we only need so much precision, okay? And so a lot of times our scales will cut this off and say that's good enough, okay? But what we have to ask ourselves, and with regards to this, is that, did you weigh exactly that? And the answer is probably not. We could always take it out another decimal place. And so the probability that you weighed exactly 120 pounds is 0. The probability that you weigh exactly 120.2 is 0. That you weigh 120.24, 0. All right. However, so you're probably asking yourselves, well, where the heck are the probabilities if they're not sitting on any specific value? Well, we could say this, is that, let's say that your weight fluctuates about 5 pounds during the year, okay? And so you could weigh, anywhere from 117 to 122 pounds, and that's typically how you would fluctuate through the year. We could say then is that the probability that your weight is somewhere between 120 and 121 pounds, that exists. Excuse me. That exists, okay? And so what we have to understand is that we can't set it to any specific value, and we will always have to work with, what does that look like to you? That looks like an interval of numbers, okay? So we're always going to create an interval here with regards to the continuous world, all right? And I have to warn you of something, okay, is that this idea flies right in the face of the discrete world. Remember I told you have to keep the rules straight for discrete versus continuous? This is the reason why, all right, is that with the discrete world, remember what we did with the discrete world? We did a probability distribution where we said we had a chart. And remember we had maybe a 0 here, 1 here, 2 here, 3 here, and then we created a probability distribution, something like this. And then we could say then the probability that x is equal to 1. We could look at our probability distribution and say, oh, it's 0.2. So in the discrete world, all the probabilities are located at exactly at these whole numbers, at 0, 1, 2, 3. Okay. However, it's exactly the opposite with the continuous world. With the continuous world, we can't say that it sits at any specific value. We have to create these intervals, all right? And the intervals contain the probabilities. And so this is the big rule between the two. So intervals for continuous random variables, okay? But specific values as far as their probabilities go with the discrete world. So you may want to review that, okay? And make sure that you have that concept down. All right, so we're going to move on to something else here. So we're going to talk about a normal random variable. A normal random variable is a specific continuous random variable. So just like how we did in 6.3 where the binomial was a specific discrete random variable, well, the normal random variable is a specific continuous random variable. Okay? And since a normal random variable is a specific continuous random variable, we have to talk about its characteristics. So let's talk about its characteristics. What would make a random variable a normal random variable? All right. 1, it's bell-shaped. 2, it has a mean that we're going to call mu. And how are we going to measure its standard deviation? With sigma. So let's see, it's bell-shaped, right? And since it has a mean of mu, we're going to throw mu then. Let's see, for any bell-shaped curve, where's the center of this distribution? It's mean. So we're going to throw mu right in the center there, right? The total area under this curve is 1. That should be obvious because for every continuous random variable, the total area under the curve is 1. Okay. 4, it's symmetric about the value of mu. That's sort of obvious now, okay, because since mu is in the center here and bell-shaped curves are symmetrical. By the way, this is perfectly symmetrical. This is not sample data. This is a model. Models are perfect in a sense, okay? And this is perfectly symmetrical. All right, it's perfectly symmetrical. So so it's symmetric around the value of mu, okay? And then the fifth one, there's one more, but I want to demonstrate that with graphs, okay? So what's going to happen here is that how exactly in these problems are we going to know that it's normal? We're not going to have you look at graphs or whatever. We will tell you in the problem. We might say, let's say that we're talking about male adult heights, okay? And we might say, well, male adult heights are normal, or they're normally distributed. Once you see that wording there, you just say, oh, okay, that means if we made a histogram for all the male heights, it's going to be bell-shaped. Okay, we're going to throw the mean right in the middle. Its standard deviation is going to be measured with sigma. Okay, the total area under its curve is 1, and that's the case for every continuous random variable, by the way. And then obviously it's going to be symmetrical about mu, and then we're going to talk about one more, but I have to demonstrate it with graphs, and so you should kind of think that. Okay. All right. Let's move on. So we have a bit of a problem here, and this kind of demonstrates the unique feature of number 5. Okay. Is every time either the mean changes, okay, or the standard deviation changes. Okay. So problem, every time either the mean or the standard deviation changes, we have a different normal random variable. So notice here that, I'm going to back up just for a second. Notice I put here a normal random variable. I didn't use the word the, I used a. What does that mean to you? Instead of using the word the, I used a. Well, that's telling you that there's a whole lot of normal random variables, okay? And there's one at every unique value of mu and every unique value of standard deviation, sigma. So every time mu or sigma changes, you get a different normal random variable, okay? But they all have the same these characteristics. So all of them have these characteristics, that they're all bell-shaped, they're all have a mean mu, okay, and so on and so forth. All right. So we have a problem here. The problem is that would mean we would need an infinite amount of tables, because there's an infinite amount of normal distributions. Every time mu changes or sigma changes, we get a different normal random variable, okay? So are we going to create a whole bunch of tables to figure this out? The answer is no, okay? And so mathematicians and early statisticians had basically a problem here. They said, okay, so every time mu or sigma changes, we can't create a whole new table. Remember, this is talking well before computers, all right? And so they had a bit of a problem. They said, how are we going to solve this, okay? And so let me demonstrate here how we could possibly solve this, all right? So let's say we go back to our problem where we had a mean of 70 and a standard deviation 4 for the male heights, okay? And let's say that we were just talking about the interval from 66 to 74. So we know that approximately 68% of the data is located between here and here, okay? And what I want to point out to you is this. Notice the z-score is from a -1 to a +1, okay? All right, sound good so far? All right, let's change it up now, all right? That was for male heights. Let's say that instead of looking at male heights, we take a look at female adult heights, okay? So now it's all the adults that are female, okay? Now what's going to happen is that the mean is going to change. It's going to be a little, in general, what happens with regards to when we go from males to females. The females are going to be a little shorter, okay? So the mean is no longer 70. It's going to be maybe 64. And the standard deviation maybe is going to change, and we'll say that the standard deviation now is 3, so sigma is 3. So we have mu is equal to 64 and sigma is equal to 3. But let's say that we still look at the area, this area right here, okay? So 64 is the center. We went out one standard deviation this way. We went out one standard deviation that way. So how much of the data is located in there? It's still what? It's still 68%. So even though x changed, what didn't change here? So what didn't change? The z-scores. The z-scores did not change a bit, okay? This is leading to our solution to the problem, okay? Even though we went ahead and changed x into something else, we still know that 68% of the data is within what? One standard deviation of the mean, okay? It doesn't matter what x is, okay? What matters is what the z-score was. So here, notice the z-scores were from here to here were consistent, and it didn't matter what the x is. The z-scores went from what? A -1 to a +1, and we said 68% of the data is located between there. Well, let's just to remind you, let's go back to the males. What do the males say? Doesn't matter what this is, okay? Doesn't matter what that is. What was consistent? We know that from a -1 to a +1, all right, how much of the data is located in there? 68%. And so what's consistent about all this stuff isn't x, because we know that x can change. X can have a different mean, different standard deviation. But what is not changing? It's the z-scores, okay? And so mathematicians and statisticians said, you know what? This is what we should do. Instead of every time mu or sigma changes and figure out probabilities based upon that, what should we do? We should figure all these probabilities out with regards to normal distributions, with regards to z-scores, and just make how many tables then? We only need one table, a table of a bunch of z-scores. And so if we run into a problem where x is normal, we don't work with necessarily, we're not going to make a table that has a mean of 70 and a standard deviation of 4, okay? We're going to make a table that is just a bunch of z-scores. And all we have to do is convert x into z. And you know what? You've already done that back in chapter 2. All right? We've already done that back in chapter 2. So that's the solution, okay? So, like I said, here's our problem, okay? Here's the solution. Create just one z-score table with their corresponding probabilities. And all we got to do is we got to go ahead and change x into z, and we can use that one table then. That's the solution, okay? So every problem that is normal, what are we going to do? We're going to change x into z, okay, and then use the table. Use that one table that we learned, okay? So, this to further understand the solution here, what mathematicians early on and statisticians early on did, they created this idea of the. Now notice here, the. What does that mean to you? There's only one. It's unique. It's unique now. The standard normal random variable. Notice I threw the word standard. We standardize the process. Okay, what's the process that we standardize? We standardize the following process, is that if we're going to work with a normal random variable, okay, that we're going to call x, if we change x into z, and use this one table, we have now standardized this process. So they decided to call it the standard normal random variable. All right, this is a special normal random variable, and it has a mean of 0 and a standard deviation of 1. And this is so special in statistics that it has its own letter that we give it. It gets its own random variable, z, meaning what? Z-scores. Okay, so anytime you see z, okay, in statistics, we're talking about the standard normal random variable, okay, and it's just it's a table of a bunch of z-scores. So we have to absolutely positively learn this table. All right. So now, just to demonstrate what I mean by a mean of 0 and a standard deviation of 1, okay, let's go back to our graph here. So here's our graph, right? So notice, don't look at x, look at z. What's in the middle here? Well, let's see. So it looks like z, since it's normal, that means z is bell-shaped, right? And what's in the center right here? 0. Okay, and so the mean of any normal random variable is going to be in the center. So, and notice, what is the standard deviation worth? It's worth 1. So notice it was worth 4 here units. This is it's only worth 1. Okay, so that's what we mean by that. The mean is 0 and the standard deviation is 1. Okay, so let's keep on going here. So we have to absolutely positively learn this table. Okay, so what I'm going to do is, I usually don't do this, but I'm going to get out of presentation mode. Okay, I'm going to get out of the presentation mode. Okay, and I'm going to go over to here and get into the table. Okay, so I highly encourage you to print this out. If you have not printed this out already, I would pause the video, okay, and take a look at physically in front of you the table, okay. And so I have in that section 6.2, I've provided you this exact table. I would print this out. You don't need it in color necessarily, but I would print this out, okay. And by the way, there's this page and this page, okay, and this is exactly from the book, all right, and it's in Appendix A, so it's 2 pages. Once you have printed this out and you have it physically in front of you, okay, I would come back to the video. So let's assume that you have this printed out, and you can easily see this in front of you now. Okay, so let's break apart this table. Okay, what exactly is it telling us? Well, first of all, notice with the big appendix A side. All right, notice that you have these values that are negative, and right here it says Z. Okay, so the Z scores on this page are negative. Okay, go to the other page. I'm gonna have to scroll down. Notice that the Z scores over here are what? They're positive. They're positive. Okay, so you have negative Z scores here. You have positive Z scores over here. Okay, that's the first thing. Second thing, remember what I told you back in chapter 2, that how many decimal places are we going to always round our Z scores to? You guys remember? 2. Okay, now you might be saying, hold on, Doug, I don't see two decimal places here. This is a units place, and this is by the way, this is a decimal right here. And so this would be like, if I was looking at this number right here, right now I'm looking at a negative 2.9. Okay, so this is only taking out one decimal place. Where in the world is the second decimal place? The second decimal places are located up here. Okay, and so this is taking it out to the second decimal place. Okay, so let's say that we had to look up a negative 2.03, negative 2.03, all right, for a z-score. So here's a negative 2.0, okay, and notice up here, here's 3. So this isn't, don't look at it, don't look at this as a negative 2.003. This is the second decimal place. You want to look at this as a negative 2.03, okay, and you would just see where they come together. There's our sound effects again. So here, a negative 2.03. What did you guys get? Did you get 0.0212? Well, there you go. Okay, so you sort of know how the z-scores work. So you got negative z-scores, okay, and you saw that on our graphs, that if it, what does it just mean to have a negative z-score? It just means that the observation is what versus the mean? It's less than the mean. And if you have positive z-scores, okay, what does that mean? Is that your observation is what versus the mean? It's greater than the mean. Okay. Okay, second thing is I haven't told you what these values mean in here. These guys in here, these guys are probability. Okay, these are probability. And you may want to write this on your graph here, on your table, excuse me, your table here, okay, is that this table is always giving us less than. It's always giving us less than. Now I have to sort of get into a place where I can draw again. So I'm going to get back into the presentation mode. Okay, so I can at least draw something here. So let's see, we'll go to the slideshow from current page here. Alright, so I got to draw again. So what I mean by this is so here I drew a bell-shaped curve, and I'm going to call this Z. I'm going to call this Z, okay? And here's 0, okay? And here's a -1, here's a -2, here's a -3. Now, I didn't space this perfectly, but good enough. This is -1, -2, -3. So we got into here at -1.43. So -1.43 is located maybe about right about there, okay? Right about here. Okay, so I'm going to draw a line straight up, and I want the probability that Z is less than that. And so I shade this in. Okay, I shade this in. And yeah, you should be doing this also. All right, you should be creating these nice bell-shaped curves and shading this in. Okay, the reason why we're shading this in is that we're trying to graphically show you what kind of answer you should be getting. So what this table is always giving us, it's always giving us the probability that z is less than some number. So if we looked up a negative 1.43, all right, that's exactly what the table is going to give us. It's always going to give us less than. It's not going to give us greater than. It's not going to give us in between, but it will always give us less than. Okay, so if your problem says the probability that z is less than some value, you can just look up that value, and there you go. Okay, so we should be able to go back to the problem here. Okay, back to the table, and look up a negative 1.43. Okay, well, let's go ahead and do that. Again, I got to get out of the presentation and go back to our table. So negative 1.43. Let's see. Oh, there we go. Negative 1.43. Right here. So maybe I'll make this bigger. There we go. Maybe that's a smart thing to do. Alright, negative 1.43. Did you guys get 0.0764? There's your answer. So the probability that z is less than a negative 1.43 is 0.0764. 0.0764. Okay. This is going to take us a little time to go back and forth between there. All right. Let's see here. This is what happens when you get to be old age. Is that what was it again? 0.0764. So I forgot what it was. Oh my goodness gracious. That's okay. We'll have to deal with my stupidity here. There we go. Okay, 0.0764. Okay, so let's go to the next problem. All right, so now we got to look up the probability that z is less than 0.48. 0.48. Now, hold on. I bet you a lot of you went straight to the table. What should we do first? We should visualize what kind of answer we should be getting here. So notice on our last problem, let's go back to our last problem. Did we shade in a whole lot here? No. Remember, this whole area underneath this curve is 100%. And what we were depicting here is that we shaded in, what? About 7.64% of the graph. Okay? Notice for this one, this is going to be a little different. So here's 0, right here. And here's 1, here's 2, here's 3. So 1, 2, 3. Notice it's a positive 0.48. So 48, that's about 0.5. So 0.48 is just a smidge that way. Okay? And we want less than. Not greater than, we want less than. So what are we going to do? We're going to shade to the left. Less than is left. Okay? So we're going to shade this in. Okay? You're going to do a better job than I am. Okay? So let me ask you something. How much area is from 0 to all, and technically this is not stopping anymore. Technically this is going to all the way to a negative infinity. Alright, so it's not stopping anywhere. So let me ask you, how about the area from 0 to all the way over to a negative infinity? That's what, 0.5, right? And so we shaded in just a little bit more than that. So maybe our answer is going to be a little bit greater than 0.5, but certainly less than 1. Okay? So we gotta look up 0.48. 0.48. Alright, so let's go ahead and go back to our table. 0.48. Did you go to the other page here? So 0.4, and we go across here up to 8. See where they come together? I got here 0.6844. Alright, so for 0.48 less than it, so this table here, Okay, this page right here is still giving us less than. Okay, it doesn't matter if the z-score is positive. This table is always giving us less than. Okay, so for 0.48, okay, we have 0.6844. Okay, so 0.6844 is our answer. All right, maybe I won't even write it. I've said it a couple of times, and you can see our answer. Okay, 0.6844. I've wasted enough time with regards to writing it. We'll just move on. Okay, let's go to the next one. Now notice here we have the probability that z is greater than 1. Now notice it's greater than. Probability that z is greater than 1.30. Now the table doesn't know that you're looking at greater than. What is the table always going to give us? It's always going to give us less than. Well, if I told you that the probability that z is less than some value is 0.9, what does that mean as far as greater than that value? Hopefully you say, well, if less than that value is 0.9, that means greater than is 0.1, because the whole area under the curve is how much? It's 1. So, in other words, we can still use the table to look up greater than. We just got to do 1 minus whatever probability that we look up. Okay? And so, let's depict this with a nice, well, it's supposed to be a nice bell-shaped curve. Close enough. Here's z, here's 0, here's 1, here's 2, here's 3. 1.3, let's see, that's 1, 2, 3. Okay, 1.5 would be about here, so we'll back it up just a little bit. 1.3 would be located here. We'll draw a line straight up to the curve. And we want z is greater than that. So I didn't shade in a whole lot, did I? So our answer should not be large. It should not be certainly greater than 0.5. Now remember what the table is going to give us. The table is going to give us from 1.3 that way. And so what is it actually going to give us? The table is going to give us the unshaded part. It's always giving us less than. It's exactly the opposite of what we want. All right? So what are we going to have to do? We're going to have to look up 1.30, see what this is, and then take 1 minus that. Okay? I'm going to have to take 1 minus that. So if you do not have your calculator handy, maybe this would be a good time to have it out, okay, and follow along, okay, because we're going to be working with decimals here. Maybe you can do the subtraction in your head, okay, but for many of us, okay, we might have to do this on the calculator. So if you don't have your calculator out, I would pause, go get your calculator, okay, and then come back. Okay, let's assume that you have your calculator now, all right, and let's continue on here, all right. Let's continue on. That means we're going to have to go into our graph and go look up 1.30. But remember, since we want greater than, okay, since we want greater than, we're going to have to do a little subtracting, okay. So let's get out of our, excuse me for the sound effects there. We'll keep our ink right now. So 1.30 we got to look up. So here's 1.3. Here's 0. So pay attention that 0 is the first one, and then the second one is actually 0.1, 0.2. Sometimes students look up the wrong value because they want to look up they look up 0.1 and they immediately go to the first column because they think the first column should be 1. Now the first column is going to be 0. Okay. So what we're looking at 1.30. So what do we got here? We got 0.9032. Okay, 0.9032 for 1.30. Okay, let's go back here. I gotta get back into my presentation and get my pen to pop up again. Okay, so now how does that play a part here? Let's see, 0.9032 is this area right here. So from 1.30 0 all the way to a negative infinity. Okay, less than. That's that area. Is that our answer? No. What's our answer? It's 1 minus this. Okay? And so you do the subtraction there. I got here 0.0968. There's our answer. That makes a lot more sense based upon this graph that we drew there. We didn't shade it 90% of the graph. How much did we shade in? We shaded in a lot less than that. And so hopefully you'll say that, okay, that makes sense, that about 9%, a little more than 9%, about 10% of the graph was shaded in, okay? And that should be a reasonable answer for this particular problem. Okay? Let's do one more that's greater than. So now we have probability that z is greater than or equal to a negative 2.03. All right, let's do this one. All right, here are my marks here. Give me some reasonable place to put our number here. So we got a negative 2.03. So negative 2.0. So here's a negative 2. So just a smidge over. I'm going to draw a line straight up. Okay, now don't go to the nearest tail because we have to follow simply that it's greater than. So that means I'm going to just use little lines here to represent. So instead of trying to shade all that in, probably even in class, I would just go ahead and sort of depict it with these lines here. So notice here, did I shade in a little bit or did I shade in a lot underneath the curve? I shaded in a whole lot. And so a whole lot in terms of probability is close to what? Close to 1. A little bit is close to 0. Okay? So I am shading in a whole bunch here, right? Shading in a whole bunch. Okay. So now, when we look this up, though, is it going to give us that shaded part? No. What's it going to give us? It's going to give this unshaded part. So it's going to give us less than a negative 2.03. So we got to keep that in mind. And let's go back to our table. All right. So negative 2. So we got to be on this side, right? This side of things. And we got to look up at negative 2.03. So here is, why don't you go ahead and look it up on your table. All right. And let's see if you get the right answer. So here's a, go ahead. So negative 2.03. What'd you get? 0.0212. Okay, just like we did before. I think that's what we looked up previously. Okay, when we started this looking at the table. So I'm putting it in my calculator 0.0212. Okay, and we'll go back to our demonstration here. Okay, we'll get my pen out, and so we know this area right here is 0.0212. Okay, is that our answer? Heck no. Heck no. Why? Because we shaded in a whole lot of this, right? And our answer should be closer to 1. And so this would be 1 minus 0.0212. And what do we get this time? 0.9. What does that look like? 788, if I did my math correctly in my head. Okay, so obviously, if you want to, if you need to use a calculator, please go right ahead. Okay, but 0.9788. Okay. By the way, can we ever get negative values here? The answer, you guys should say absolutely not. These are probabilities, and what are always probabilities are always between what and what. They're always from what to what? 0 to 1. So you can't have negative. You can't have greater than 1. Okay, so if you ever get a probability from this table that's negative or greater than 1, we've done something wrong. Okay, All right. Let's see if you remembered a concept. What would this answer be? So don't take a look at this stuff here. Okay. Let's take a look at this right here. So we had in our previous problem greater than. Okay. Notice I changed it over to just we had greater than or equal to. Sorry. We had greater than or equal to, and now I've changed it just to greater than. What would this answer be? Okay, what would this answer be? So this is what we just looked up. Okay, this is just what we just looked up. But what would this answer be? So let's take a look here. Let's go to the next line here. So what I've done here is that the probability that z is greater than or equal to a negative 2.03 can be separated into two pieces parts. It can be separated into the probability that z is greater than a negative 2.03 plus the probability that z is equal to a negative 2.03. Okay, so all I did was separate the greater than and the equal to into two equal parts and put a plus sign in between them. All right, that's all I've done. All right. Well, what did we say the probability that any continuous random variable was equal to a specific value? What did we say at the beginning of the presentation? Do you remember? So remember, z is the standard normal random variable. That means it's a special normal random variable, and normal random variables are continuous. So the probability that z is equal to any specific value is what? It's actually 0. This is 0. So if this is 0, okay, that means the following. The probability that z is greater than or equal to a negative 2.03 is exactly equal to the probability that z is greater than negative 2.03. That's kind of weird. We're not used to such things, but that's absolutely true in the continuous world. Now, in the discrete world, you have to pay attention to, is it greater than or equal to? But you know what? In the continuous world, it doesn't matter if, so in other words, if we went back to any one of these, okay, if I put an equal to sign down here, does it change the answer at all? No. If I put a equal to sign down here, did it change the answer? No. If I put an equal to sign down here, did it change the answer? No. And if I got rid of the equal to sign, did it change the answer? No. It doesn't change it. It doesn't matter if it's less than or equal to, greater than or equal to. Excuse me. It doesn't matter. Because there's no probability sitting exactly at that value. So we'll keep on talking about that as we go along, but it doesn't matter if you have the equal to sign in the continuous world or not. It just doesn't matter. Okay? But that, again, is just for continuous random variables, not for discrete. Okay, so we can run into one other type of interval. Okay, notice z now is what? In between two values. All right, it's in between two values. So let's depict it. Here's 0. Here's a negative 1. Here's a positive 1. We should already know what our answer should basically be. This is the empirical rule, right? And so this should be about 6 to 8%. So we're going to see where exactly this is coming from. Okay? All right. So how can we use the table in order to figure this out? So we want the area in between, right? And we already know that this is roughly 6 to 8% of the data. Okay? So how can we use our table to figure this out? Well, remember the table is always giving us less than. Okay? So there's a couple of ways that you can figure this out, but I'm going to give you the most straightforward way of doing this. What I would do is I would always look up the number to the right. Doesn't matter what it is. I would always look up the number to the right first and look up that probability. Now, what would that mean graphically? What that would mean is that we just looked up the area from 1 all the way over to a negative infinity. So, in other words, if I was able to shade it in, I would have, if we looked up 1, we would be looking up the area from here all the way over to a negative infinity. Okay? But we were supposed to stop at a negative 1, okay? And we didn't stop, right? So, it sounds like we need to subtract something. And what do we need to subtract? We need to subtract off this area. So notice, if you have this area and subtract off this area, what are you going to be left with? You're going to be left with the stuff in between. So this minus that should give us what we're looking for. All right? And what is this area associated with? Well, believe it or not, it's just associated with that number right there. The area to the number on the left-hand side. And so whenever you have something in between, the way to go about this is that first you look up the number on the right, and you know that's a little bit too much area. Then you look up the number on the left, and that's the area that we have to subtract. Okay? Please, by the way, do not subtract z-scores. That will not work. Okay? It is subtracting off the areas, the probabilities. All right? And so, let's go back to our table. And let's look up a positive 1 first. That was the number to the right. So we're going to have to be on this one. Okay. And so what do we get here? We get here, let's take a look, 1.00. So I got here 0.8413. 0.8413. Okay. Then we would have to take a look at, and so maybe when within your notes, go ahead and put down 0.8413 so we don't forget. Okay. And then let's go ahead and look up a negative 1. So we know that this first column is 0.00. Okay, so negative 1 is 0.1587. Okay, do you guys see that? All right, so I think we have our two numbers now. So let's go back to our presentation here. Let's get my pen out. So we got here from here all the way over. It's what, 0.8413. Now I'm not saying that's the middle part. I just needed some room to write that down. That is from here all the way over. Okay. What about this area right here? That area is 0.1587. Okay? And what do we got to do with these two numbers? We have to subtract them. So you would take 0.8413, the larger number, and subtract off the smaller number. And see what you get. Okay? So let's see what we get. When you put that in your calculator, you get 0.6826. There you go. 0.6826. In other words, approximately what? 68%. So that's why we say it's approximately 68%. And actually, we could take this out a lot more decimals. Okay, a lot more decimals. And but generally speaking, 4 decimal places is good enough. By the way, when we work with z-scores, okay, we figure out probabilities, do not round any of these probabilities. Keep it to 4 decimal places. Do not round the probabilities to 2 decimal. The z-scores themselves, 2 decimal places. But as far as the probabilities go, leave them as 4 decimal places. Please, please, please leave them as 4. Okay, don't round. So don't say it's 0.68. Say it's 0.6826. Okay, we want it out to 4 decimal places. Okay. Okay, so would it have mattered if I put a greater than sign here? Nope. Would it have mattered if I an equal to sign here? Nope. Does it matter if I put an equal to sign here? Nope. Okay, so it wouldn't matter if I had that. It's still going to be equal to 0.6826. Doesn't matter if I had that. It ain't going to matter, right? Okay, let's move on. Let's say that we had to look up this one. Okay, so now See if I can do a better job of making a picture here. That wasn't too bad. Here's z. Oh, that was bad. I had to mess up something, didn't I? Here's 0. Here's 1. Here's 2. Here's 3. Now, I'm putting in this whole thing now, the whole scale, because we are working with both negatives and positives. Actually, if I was in class, I would probably put the whole scale, no matter what problem we were working with, but it's a little harder here and takes up a lot more time. So now notice here that that both of these numbers are negative. That's okay. So let's see. I don't care where we start. We can start with this number and put it on our graph. So negative 2.26. Maybe, let's see, that's about a quarter of the way down. So maybe about right there. Okay. Negative 2.26 and then a negative 0.54. So there's a negative 0.5, maybe just a smidge over. 0.54, we'll draw a line straight up and down. Okay. And so what are we looking for? We're looking for this stuff in between. Okay. And certainly our answer should be, since both of the values for z are both negative, that means our answer's got to be less than 0.5. Because remember, from 0 all the way over to a negative infinity is 0.5, and we shaded in a little less than that. Okay, so our answer should be less than 0.5. Okay, and we can see that from our graph. So we got to go ahead and look up a negative 2.26, and we're going to also have to look up a negative 0.54. Okay, so let's take a look and see what we get. Okay, so we're going to get out of this. But which number are we going to look up first? We're actually going to look up 0.54 first, right? Because remember, that's going to be from here all the way over to negative infinity, 0.54. And then we got to look up negative 2.26, and that could be from here to there. And we got to do a little subtracting. Okay. Okay, so let's look up a negative 0.54. All right, so now maybe I have to make this a little, I got to back off a little bit so we can see the top of our table here. There we go. I think that'll work. All right. So here is a negative 0.5. Here is, oh, right here. Here's 0.4. So we see where this comes together. Okay. And so it looks like we have a value there of what, 0.29. Let's move that down just a little bit. 0.2946. 0.2946. So I'll have to write that one down somewhere. 0.2946. I just wrote it down so that we remember. Okay. 0.2946. Let's go with negative 0.54. Let's just make sure we got the right number. Yep, 0.2946. Okay, so then we got to look up a negative 2.26. Okay, negative. So we don't have to go to the other table, right? Other page. We can stay on this one. Negative 2.2, and over here is point. Oh, for goodness sakes! There we go. 6. Negative 2.2. All right, 6. Do you see the value there? I got here 0.0119. So I'm writing that down. Okay. So those are the two values that we're going to need, and we're going to have to do a little subtracting. So negative 2.26. Just make sure I got the right number. Yep. Okay. All good. Let's go back. Let's get back into the presentation. I'm sorry, I know it's very clunky, but to put this table in, I'm going to have to maybe find a different way to do this later on, because we're going to have to work with the standard normal table again. I'll have to figure out a way to do this so that I don't have to keep on going back and forth. But for right now, I think this is okay. So we have our two numbers, right? We had from here to here, 0.2946. Okay, and that's a little bit too much area because we were supposed to stop right there, so we needed to subtract off this area. Okay, and that turned out to be 0.0119. Okay, so we got here 0.2946 minus 0.0119. Okay, let's see what we get here. I suppose I could do that in my head, but 0.2946 minus 0.0119, but it's early in the day, so I'll just let my calculator do the work here. So we got here 0.2827. That makes sense. Let's see. Yep. Okay. There's our answer. So from here to there, we have about, this looks like 28.27% of the data. Okay? And that would be our probability. By the way, notice I didn't even bring up that we had an equal to sign down here, because it doesn't matter, right? It doesn't matter if there's an equal to sign down here. It just doesn't matter. Okay? Not in the continuous world anyways. So, here's the thing, is that with regards to then working with the standard normal table, okay, we can do any problem now that's normal, okay? So let me show you. So what we have to do now is when we work with any other normal random variable, it's not going to be a standard normal. It's going to have like a mean of 70 and a standard deviation of 4, whatever, right? And so how did we change x that is normal, okay, into standard normal variable? Now, how do we do that? How do we change that? Well, remember back in chapter 2, we worked with this formula, z is equal to the observation minus the mean divided by the standard deviation. Sound familiar? Well, guess what? We're still going to be working with that formula, all right? So we're still going to use this formula. It's just that, what are we going to do? We're going to use symbols in chapter 6. That's all. And so the observation, what you got to think of the observation as, is just simply x. Okay? And the mean, what's the mean? The mean is mu. What's the standard deviation? Sigma. Standard deviation is sigma. Okay? So there's the formula that we're going to use in chapter 6, but it still follows this basic formula that we used in chapter 2. And so to change x into z, okay, notice z would be equal to x minus mu divided by sigma. That's the formula that we're going to use in chapter 6, but it still follows this basic idea. Observation minus the mean divided by the standard deviation. So let me give you an example. So, it says here we're going to apply the standard normal table, okay? It says here the diameter of a certain type of tree in a forest is normal. Remember what I told you? That you're going to see that in problems, okay? You're going to read that. You should say to yourself, oh, okay, diameter of a tree is our random variable. That's the thing that's changing from person to person, or in this case, thing to thing, okay? And that's x, okay? And that is x for the problem. So notice here I put tree diameter for x, okay? And it's normal. That means if we put all these tree diameters into a histogram, it should turn out to be a nice, what? Bell-shaped curve with all the characteristics of a normal distribution. So here's x, okay? Let's keep on reading here. This is with a mean of 34.5 centimeters and with a standard deviation of 8.4 centimeters. And so what did we say there? Mu is equal to 34.5. Oh, then let's keep on reading here. It says, assume these values are for all the trees of this type in the forest. That's why I made this mu, and that's why I made that sigma. So we're talking about all the trees in the forest, okay? So let's say mu is equal to 34.5, sigma is equal to 8.4, okay? So that means we would put 34.5 right here, okay, right in the center. And I'm not going to do this, but you could take this out 8.4 units here, 8.4 units here, 8.4 units there. Take it out 8.4 units this way, there. Okay, see what I'm doing? All right. And the question says, what's the probability we randomly choose a tree of this type and has a diameter greater than 50 centimeters? So in other words, what are we doing? We're trying to figure out the probability that x is greater than 50. X is greater than 50. Okay? Okay. Now, the question is, do we have a table where a normal table with a mean of 34.5 and a standard deviation at 8.4? Heck no. We don't have that running around anywhere, right? So what do we have to do? We have to convert x into z. And then after we convert x into z, we can use our standard normal table that we've just been working with. Okay? So believe it or not, there's only one extra step here. What's the extra step? And you guys already know how to do this extra step. You got to take and change your x into z by using our z-score formula. That's all. Okay? What's the value that we're going to throw in for x? Whatever this is right here. So we're going to throw in there 50 for x. What are we going to throw in for mu? 34.5. And what are we going to throw in for sigma? 8.4. Just keep your calculators out because we're going to need them. Okay? So, let's go ahead and actually figure that out. So we got 50 minus 34.5 divided by 8.4. Now, remember, we have this line going straight across like this. What does that mean about the numerator? We should realize that we need to put parentheses there. So I'm going to put parentheses here to remind you that when you put it in your calculator, you got to put parentheses there. Okay? You can't put in your calculator 50 minus 34.5 divided by 8.4 because your calculator is always going to follow the order of operations. So it's going to do the division first and it's going to give you the wrong answer. So when you put this in your calculator, you're going to have to put it with parentheses, okay, in the numerator. Okay. So when you go ahead and put that into your calculator, that should have come out to 15.5 divided by 8.4, and I got here 1.845 when I calculated it with my calculator. Okay. So I'll wait for a second here and make sure that you are comfortable with that calculation. So I got here 1.84523800952, but I don't care about all those decimals, so I want to round it to 2 decimal places or z-score. So all I'm going to do is I'm going to look at the third decimal place, and the third decimal place is a 5. Okay, it's a 5. So since it's a 5, we're going to round this up to 1.885. Okay, so I rounded the 4 up to a 5. Okay, so there's the z-score that we're going to be working with. Okay. So you know what that just did? We just translated x, which was greater than or equal to 50, into, well, how far, how many standard deviations is that away from the mean? And it turned out to be 1.85 standard deviations. So what just happened here is that x is now z. We translated x into z. 50 translated into 1.85 standard deviations away. Okay. And by the way, does anybody remember when this inequality flips on you? You worked with that in a lot in algebra, okay? And inequalities. Does anybody remember when the inequalities flip? It's when you multiply or divide by a negative number. And we are dividing by something, dividing by sigma. But sigma is always going to be positive. So in other words, you're always dividing by a positive number. So what's going to happen in the sign? Nothing. It's never going to flip on you. So if it starts as a greater than, it's going to stay as a greater than. Okay? So we don't have a table, a normal table of where mu is equal to 34.5. We don't have and certainly we don't have a table that has a sigma of 8.4. But we do have the standard normal table. Okay? And so notice, can we look this up? The answer is, of course we can. Okay? And so let's go back just for a second to here. Okay? So that meant that our value of 50 was located about right here on the table. Why? because this is 1, this is 2, this is 3, okay? And so it looks like, because we were, what, 1.85, right? 1.85 standard deviations away, okay? So graphically, we want greater than that, so we would fill in this area right here, okay? Does that look like a big area that we're filling in? It doesn't look like it to me, okay? It doesn't look like it to me. And so what are we going to have to do? Let's see, we want greater than, and so remember when we look up on the table, it's always going to give us less than. But we want greater than, so we got to do what? 1 minus the probability. So we got to look that one up, okay? Go ahead and look that one up. I will do the same. I'll have to get out of the presentation again. And let's look up a positive 1.85. 1.85. So, 1.85, there we go. So 1.85, I got here 0.9678. That'll be an easy one to remember. 0.9678. Okay? That's not our answer, right? Because that is giving us less than. That's giving us less than. That's not what we want. Okay? So we know that this area right here is 0.9678. But we want 1 minus that, right? And so what exactly is our answer? So you put that in our calculator, 1 minus that, okay? And what do we get? We get, I just put it in the wrong value. There we go. I got here 0.0322, okay? 0.0322. And oh, by the way, I went ahead and actually made a better picture of this. Okay, so notice here was our value of 50. Okay, and it's just short of 2 standard deviations away. So at 1.85, we have just a little bit of the area depicted. And notice here our answer turned out to be 0.0322. Okay? So that's what you're going to do. You standardize the process. You change x into z. That's all. Okay? And do another one? We'll do another one. B. Notice same background information. Okay? But B now was the probability we're going to choose a tree has a diameter less than 30. Less than 30 centimeters. Less than 30. Okay. So we saw the mean is 34.5. We still have a standard deviation of 8.4, and we're trying to figure out the probability that x is less than 30. All right, so let's see. We're going to have to plug in 30 for x. We still have our mean of 34.5. We still have our sigma of 8.4. Okay. So put that in your calculator, 30, remember parentheses, 30 minus 34.5 divided by 8.4. So we get a negative 4.5 divided by 8.4. And when I originally did this, I got a negative 0.535, but we don't want our z-scores to be 3 or 4 or 5 decimal places. We want our z-scores to be how many? 2. We want our 2 decimal places. Okay? And so I'm doing that calculation again in my calculator. So I got here 0.53571.4. Don't care about all those decimals because we just want to round this to 2 decimal places. So we're just going to look at the 3rd decimal place, and we're going to round properly to a negative 0.54. So there's our z. Okay, and that means now we're going to use our standard normal table. And you know what? I'm not going to depict this by hand. I'm just going to allow the computer to do this for us. So remember, we were looking for the probability that x is less than 30. So here's, in terms of x, here's 30. Okay, in terms of z, that turned out to be almost, let's see, a negative 0.54 right here. Okay. So can we look this up? Can we look that up on our table? We most certainly can. So let's go look up a negative 0.54. Now, remember, it's less than, so do we have to do any subtracting? No. Remember, the table's always giving us less than. It's always giving us less than. So let's take a look. Negative 0.54. All right. There we go. Just makes it in my screen. So here's a negative 0.5. Here's 4. I got here 0.2946. 0.2946, and there's our answer. That's all. 0.2946 would be our answer. Okay. 0.2946. So less than, you always get to just look it up. Remember, so x changed into z, 30 changed into a negative 0.54. We keep our sign. Okay? Last one. What's the probability we randomly choose a tree of this type and it has a diameter between these two values of 35 and 45? All right. So here, we would write this as 35 less than x less than 45. Okay, so that's what we're looking up. So what do you think we're going to have to do here? What we're going to have to do is we're going to have to do the z-score formula twice. We're going to have to change 35 into a z-score. We're going to have to change 45 into a z-score. All right. So let's do that. So we have z is equal to 35 minus 34.5 divided by 8.4. What do we get? I got here 0.06, rounded, I think, properly to 2 decimal places. I'm going to have to do this for 45. Okay, I came up with 1.25. I think it's exactly 1.25. So there's no rounding necessary here. So what does that translate into? That translates, so 35 and 45, that changes into 0.6. And 1.25, so x is now z. Signs aren't going to flip. Now, can we look this guy up? Can we look that one up? And absolutely, we can look that up based upon what I showed you maybe 20 minutes ago. So on a depicting this, okay, what do we got here? Let's see. We were trying to change 35 and 45, so here's 35 in terms of x. So this is x. So 35 and 45. Oh, I got a mistake here in my presentation. That's not correct, but I'm not going to do this over. I've been doing this now for 45 minutes. That was incorrect. What do we have to look up? We actually have to look up from here to here. So that was a leftover from my last slide. So we have to look up from 0.06 to 1.25. Okay, so we have to look up 1.25. So let's write that down. Right, we got to look up 0.06, and we got to look up 1.25. Okay, so let's go ahead and do that. We'll keep that, and we'll get over to here. Okay, so 1.25. We have to look up first. Remember, that's the number to the right. So 1.25, I got here 0.8944. 0.8944. We'll write that down. Okay. What else we got to look up? We got to look up 0.06. Oh, now be careful with this. It's not 0.6. It's 0.06. I got here, that would be this number right here, this 0.5239 number. Okay. You see why it's not 0.6 and it's you got to look up 0.06.5239. Okay? Okay. Let's continue here. Got to get back in the presentation. I'm sorry about my little mistake there. I don't think that's going to throw anybody off. Alright, let's move on here. So we're going to apply the standard normal table. Alright, and so notice those are the numbers that we looked up before. We had 0.8944 minus 0.5239, and I got an answer of 0.3705. 0.3705. Okay? So that was the third example. So we did less than, we did greater than, we did in between. And again, it wouldn't matter if I had a equal to sign here or equal to sign here. No, it's not going to change anything. Okay, the probability is not going to change if we're looking exactly up 35 or 45, because there's no probability sitting there. Okay? So, I know that was a long presentation, but I think that ends our discussion with regards to 6.2. All right? Thank you for your time.